we are going to talk about the reaction kinetics in food quality. So, in the earlier lecture we talked about the food safety and looking at the reaction kinetics. Now, we are going to talk about the kinetic approach for estimating food quality. So, if you look at food, it is a highly complex biopolymer. In addition to microorganisms, food probably contains a lot of different materials, like you may have vitamins, you may have proteins, lipids, carbohydrates, and when you are heat processing it, pressure processing it, it's going to produce a lot of changes. So, the quality of the product you are processing depends on how much time you exposed with heat, pressure, number of things, and what changes you are causing them. And in addition to that, a lot of the fruits and vegetables, they also have enzymes. These enzymes also probably cause deteriorative reactions in addition to the spoilage microorganisms. So, you want to kind of control them. So, for that you need to look at the enzyme inactivation. When you are heat processing certain substances, like for example sugars or lipids, proteins and so on, you may have certain crystallization, aggregation of substances may take place, and as a result you kind of trying to have understanding of how these different components going to affect your product quality. So, if you look at the reaction kinetics, we talked about microbial reaction. The biochemical reactions also have a similar concept, except it may be using more chemical reaction kinetic equations we used earlier. And some of these reactions may be reversible or reversible. In other words, you may have enzyme completely inactivated, or the enzyme may inactivate and then maybe recover if there is a need. And it also depends on the treatment intensity and the storage conditions. So, for example, if you are storing at 5 degrees Celsius, the quality of the product probably going to be remains much better, because at low temperature some of the deteriorative reactions going to be less. So, you can able to store for a longer time. Whereas, if you are going to increase that to room temperature and you do not have appropriate packaging material, you may deteriorate much more quickly. So, during the break I had a conversation about accelerated storage studies, where somehow some of these deteriorative reactions can happen, and how you can able to minimize those, and how do you predict some of those things with the shelf life testing. So, the goal here is we kind of develop process condition where we want to have some of these reactions can be desired. So, you can able to increase them, whereas some reactions are undesirable, you want to kind of reduce them to the extent possible. You may not be able to completely reduce the reactions, but you can try to minimize them to the extent possible. So, if you look at different substances, like for example protein, it may go through various reactions, like it may denature, it go through hydrolysis, it may have certain Maillard reactions and so on, and that may result in precipitation, solubility, and you may have some anti-nutritional factors, for example in some of the plant proteins and so on. Whereas, if you have certain vitamins, you may have oxidation, and then you are going to lose the nutrition value and so on. So, you kind of look at different products, different components, and then try to understand how some of these chemical reaction kinetics can help you to have much more stable product. So, chemical reaction kinetics use a different set of mathematical equations, and so essentially suppose I have a particular product with a certain concentration, and I'm going to process for a certain time, and I'm going to generate a curve, and then in this curve I'm going to calculate the slope, and then that slope is going to give my reaction rate constant. So, this particular value, maybe I have certain ascorbic acid in maybe in a juice, how much ascorbic acid initially I have, and then as I am heat treating that, how that ascorbic acid kind of reduce. And initially it may have certain concentration, and then with time how that change over particular time at a particular temperature. A general form of equation is the change in concentration with time is a constant K, C, that is a concentration, and then a term N. And then depending on different reaction rates, like you have 0 order reaction, first order reaction, second order reaction, different reactions can come in the system. So, 0 order reaction basically assumes that the rate of reaction is independent of concentration of the material. So, in other words, I have certain concentration of my ascorbic acid, and then that change in ascorbic acid value with time is independent of concentration. So, if I had 100% concentration, or I had 75% concentration, or 50%, it's immaterial. It's going to decrease maybe 5% every minute I'm processing. So, then you can able to say dC over dt is just a constant 0, and then by solving this equation you have this relationship C minus C0, that is your initial concentration, and then you are going to reduce over time certain value and then get this. And so you can able to get this type of 0 order reaction. So, when you have, for example, non-enzymatic browning of whey powders, things like that, you can see that this is kind of follow 0 order reaction, and then for each temperature you are going to have certain K value. So, you can able to get that value. The second one, the value is going to change as a function of concentration. So, in other words, if I start with 100% orange juice, or I start with 50% orange juice, the degradation rate may be different depending on my starting point. So, you may have more degradation in one case and less degradation in second case. So, this is where you are relating the degradation with the time as a function of both the rate constant and the concentration here. So, this is your first order reaction. So, here some of the typical problems this may use this type of first order reactions are when you look at degradation of color pigments, enzyme inactivation, things like that, you are going to have first order reaction. So, in other words, the rate of degradation of enzymes is not only dependent on the time, but it also depends on how much quantity of enzymes initially I had and so on. So, it can kind of lead with that type of thing. And then the same with the truth with the color pigments. Then you can keep going second order, third order, nth order and so on. But normally in food process operations, you are going to have 0 or first order reactions, and then you can kind of do that. Now, if you are a beginning user, one of the questions people always ask is, you have a raw data, and then how do I decide it's a 0 order or first order? So, one way to probably look at is, you can do a set of experiments and then you can plot them but both 0 order and first order, and then see whether it makes sense. So, if you look at this data here, the data sets here, you can see the data present even here. Whereas if you use a 0 order, you are you are saying everything is kind of completely depleted in 200 days, whereas in reality, even in 300 days, you have something there. So this is much better fit with the first order reaction and so on. So by simply mathematically playing with these type of orders, you can see which one your particular reaction may be much more suited and so on. So this is regarding the second order reaction, and again you can have a solution, and then you're going to have a hyperbolic relationship between the concentration of the reactant and time. So previously the concentration is just first order. Now here it's a second order, so you're going to have a parabolic relationship. But this type of reaction is not that common in food processing, so probably for most of the operations you don't need to worry about it. But one example is lysine loss in milk, maybe kind of give an example for second order reaction. And for the sake of completeness, you can think about nth order reaction, which can be related like here, so that you can probably get this type of things. But more commonly, 0 and first order are much more common in food process operations. The next concept we talked earlier is the activation energy. So activation energy is the minimum energy required to start a chemical reaction. So when you are kind of heat treat or when you are doing different processes, to initiate a reaction you need to provide or supply certain energy, and so what is that minimum energy is the activation energy. So the relationship here, the reaction constant K is related to activation energy EA and R, which is the universal gas constant, temperature T, and then you have a constant A0. And then you can kind of simplify this with the logarithmic graph, and then you can able to get the slope EA over R. That kind of gives you how different reactions going to affected by this activation energy. So this here the activation energy values for different reactions are given. So if you look at here, protein denaturation 350 to 500, and if you look at spore destruction 250 to 335, whereas if you look at enzyme reactions 0 to 34 and so on. So in other words, if you look at some of these things, some of these reactions probably going to go much more quicker, whereas the spore destruction going to take much more energy, whereas the other things like protein denaturation require even larger amount of energy. So the Q10 is basically a empirical relationship that can relate what happens to a chemical reaction when I change that to from one temperature to higher temperature. So let's assume that I am processing at 70 Celsius, and then I increase the temperature to 10 degrees. So that means from 70 to 80 Celsius. What type of changes probably happening? This may be related to the enzymes, flavor, degradation, enzymatic browning, and so on. Then you can say that based on those changes, for every 10 degree change, it may increase the shelf life by certain factor if I have a Q value of 2. So in other words, you calculate the reactions Q10. So at reaction temperature 1, reaction temperature 2, and if this value is 2, then in this case if I change that value by 10 degrees, my reaction is going to increase, our shelf life is going to increase the factor of 2. Now what is shelf life is defined, right? Again, shelf life defined meaning may be different to different people. Some cases it's simply a microbial reduction. So I have certain microbial reduction. If I increase that microbial reduction, or I get the microbial contaminants, then my shelf life is over. In some cases, I have certain nutrient, so I may have certain ascorbic acid, and if the ascorbic acid falls below certain value, my shelf life, I can define that's over. In a different sense, I may say, okay, if the shelf life is limited when the consumer acceptance is below, that becomes much more subjective. That may not follow these type of things. When some of these select choices are based on chemical deterioration, based on nutrition or texture change, color change, all those things, or based on the microbial, then you can able to use this for doing shelf life testing or estimating the shelf life and so on. Whereas if it depends on sensory, then whole set of parameters come in, right? If your audience is young population, or if your audience is mature adults or senior citizen, the expectations, desired characteristics, all those things can be different. So you may have to use a different set of criteria for those type of conditions. So mathematically, the shelf life can be Q10 can be calculated using this relationship here. You have activation energy EA over R, universal gas constant, and then you have two different temperatures where you have done these type of things. And in the past, I think, for example, U.S. Army for their meal ready to eat MREs publish a lot of shelf life studies, because when you have a product with a shelf life of say 1 year or 180 days, you have a longer time, and you don't want to sit and do those experiments for 2 years to see what happens. So what they try to do is they arbitrarily pick certain higher temperatures. So for example, instead of 25 degrees Celsius, they choose a temperature 37 Celsius. Then you're going to have set of kinetic parameters for microbial destruction or enzyme or quality destruction. Then they led that back to the changes happening at 25 degrees Celsius. So that way they can able to say, okay, if you're going to have 37 degrees Celsius, my shelf life is so many days, then that's equivalent to a shelf life of this in 25 degrees Celsius and so on. This topic was very popular in the 1970s and 80s. There's a professor by name Ded Labusa. So he has published a lot of different papers on shelf life testing. So if you are interested, you can probably take a look at some of the papers. I think I have one reference cited in the reference list as well. So here's just a given example problems here. So I have a sucrose, it's being inverted at 80 degrees Celsius. It's probably about 50%, and the time is about 9.1 minutes, and then 90% after 30.3 minutes, 99% after 90 minutes, and then you calculate the reaction rate constant. So in many of these problems, you kind of take that problem, read them, understand the concepts, and then put them into some type of table so that you can able to make a graph and then do your calculations. So you have processing time or the time, and then your concentration, and then you're doing the logarithmic concentrations, and then you're going to plot them with the time, and then you're getting your slope, and then that's going to give you your k value constant. And again, some of these things you can probably go back and try to do by yourself, so that if you are not done already. And again, those of you have taken engineering classes, you probably have gone through these type of exercise before, so it's nothing new for you under these conditions. Why do we do this type of calculations? So in this previous example, so basically what we are talking here, this type of experiments, what if I want to know what the concentration at 15 minutes? Because here initially we were doing at 9, 30 and 90 minutes. Now I want to find at 15 minutes, which is between these two values. So once you have an intermediate value, you have the equation, you don't need to do the experimentation. All you have to do is you kind of identify your processing time, 15 minutes, and then you substitute the values, and then you already have the k values calculated earlier. Then you can able to calculate 0.32. So in other words, these type of kinetic equation help you to find out what if type of scenario. So what if my values changes when my concentration is increased, or what if I'm going to treat this many minutes and what happens and so on. One case in this example you don't want to use. So for example, I have a processing time here, say 0.9 to say 90 minutes, but if I want to find out what is this value, for example at 100 minutes or 120 minutes, this is not good because you are going to extrapolate that calculation. Because when you do these calculations, you are going to estimate your slope based on certain curve fitting in a certain region. And then when you are extrapolating here, this data may go linear, or it may go like this, or you may go like this. We do not know. So extrapolation of this data is always discouraged. So you don't want to extrapolate that information, but within the data set you can interpolate and then able to make the estimation. But this is a common mistake number of people make, so make sure that you don't do that. You have another problem. You have different temperatures, sucrose concentration and k values are given. You want to calculate activation energy and then reaction rate at 383 Kelvin. So all these example problems try to make you to go through use the equation, get the values so that you get a practice of solving them. So you have the temperatures given, k values given. So you're going to plot the values in the graph, and then you're going to calculate the activation energy as a slope, and then you will estimate the value. Once you have the activation energy, you can able to formulate an equation, and then you can able to estimate the value at particular temperature. So here you have this slope, and then here you have the EA value, because you're going to assume that the R value is a constant. Normally you can able to obtain from reference books, or it may be, if it's in the exam, it may be given. So you can able to calculate your k value, and then once you have this value at 383 Kelvin, you can able to calculate this as the value. So one thing I noticed here, if you look at the data here is between 273 to 323, whereas I'm asking here to calculate 383. So I'm kind of violating my thing, but not all the time. This is a math equation. When you put the numbers, the math is going to give you some numbers. It may work fine because the relationship linear, and you extend this, it still may linear, but you also have a chance it may go through a nonlinear part. So it's always good practice, do not extend that relationship, because when you do calculations with the calculators, they always give out some numbers, and if you don't relate the number to physical reactions, you may just very confidently say my reactions are right, but it may not validate what's happening in real life. So you always check, is it reality happening there or not. So again, this is just an example problem. Again, you have kinetics of polyphenol oxidase in mushrooms is assuming first order reaction. You have rate constants given 0.09213. Calculate the activation energy for inactivation of polyphenol oxidase. Again, you can probably look at these values and then use this relationship to calculate the slope, and then once you calculate the slope, that value is EA over R, and from there you can estimate your EA value, activation energy value. So these are just some references. So this is one of the classical thing on chemical kinetic iteration in foods, and I think it's published in Journal of Chemical Education. I think there's a free PDF you can download from the internet, so you can probably take a look at that. This is also another good paper on kinetic modeling, and it's also published in Comprehensive Reviews in Food Science and Safety. So these two probably may be a good source for you to learn more about this topic. With that, I think we can probably stop here, and then we can have some discussions. Again, the topic of chemical kinetics is so broad, but I'm kind of trying to cover them in a shorter time. But I think once you understand the basis, you can probably get into other details more later.
Sir, I have only one doubts. So basically, when we design any equations, so we mostly prefer the zero order modeling, first order and second order linear equation. But mostly in ideal situation, we are preferably go for zero order or linear equation. But in practical scenario, it may be non-linear equation. Can you suggest any software or any kind of things where we can generate new equation like non-linear equation instead of linear equation, which can be found in everywhere? So
right. Like again, some of these things, it all depends on how much data you have to process. Excel itself can probably provide some of these curve fitting and slopes and so on. And then you can also probably use what if scenario, like for example, you ask the software to fit this with a zero order, first order, and then try to make a plot with the zero order, what type of predictions it has over time, whereas first order, what type of prediction, and then you can able to get that. So one of the challenges, of course, is how much data you collected and then how much duration is there. So for example, if you have to do an experiment for 365 days and then you only had 180 days data, and you may fit that as a zero order reaction, but when you conduct the whole set of experiments 360 days, it may become a first order reactions. So you may be underestimating certain values under those conditions. So you have to kind of look at the comprehensive picture. And from an industry point of view, a lot of times they prefer simpler is better. So you don't want to have second, third, or fourth order. It may look fancy from a math point of view, but they want everything simplicity, because what they want is in real life is that match the reality of physically what's happening in the food.
Most of the time I found either zero order or first order is the best fit model.
Right.
So mostly when we are applying some new model, we are trying to develop a new model. So for that we mostly using Origin or some kind of MATLAB also there.
Right.
But still there is a problem to develop in a new equation.
Right. I think the simpler answer is, from an industry perspective, keep it simple. Zero or first order is much more easy to understand and describe, so you can able to do that. Whereas once you get into nonlinear, third, fourth order and so on, it's mathematically difficult. So I think try to avoid to the extent. It may be interest from an academic point of view, but it may not be much value in a real life situation.
Hello, sir. So, as you told about the example of army, sir, the army that they are looking for the greater self life. So, why industries are not preferring for the greater self life in the for the common people? Did they are afraid about the over processing, or the cost is the major factor behind it?
Right. So shelf life, what do you need the shelf life, right? So from a consumer point of view, so they are going to look at the product and they have the interest to get the product consumed immediately. So if I'm going to buy a gallon of milk, I want to see maybe is it processed yesterday or last week. I think it's good. Whereas if I have that milk processed 3 months or 1 year before, I have in my mind something wrong with this milk. This is a very old milk, so something may be wrong, and those type of things. From a food science or engineering point of view, you start with a certain quality of the ingredient, and then you, through packaging and processing, you protect that quality without any changes. That milk is same as whether you purchased 3 months ago or you purchased today, because the quality doesn't change. But the consumers have this perception, right? So the commercial processor, they are interested in selling to the consumers and catering their needs. So that's where I think a lot of times the shelf life, they primarily look at things from a what they call how much time to transport from the factory to the store, and then how much time they have to have it in the consumer shelf, and so on and so forth. Now, here we are getting into a different discussion. What is the best buy? What is sell by? All those things. Because again, that's much more subjective. Because from a best buy point of view, it just says that if I buy the milk as an example, this tastes good from a quality point of view if you consume within that time from a sensorial perspective. But maybe you keep the milk for another 2 weeks. From a microbiological point of view, that milk is still good, but consumer doesn't know microbiological quality or sensory quality. They see it, then they throw that milk away. So that's kind of totally a different discussion.
Dr. Bala, I have two questions. The first one being, how do we decide whether we should use a factor of 2 or a factor of 3 for accelerated shelf life studies when it comes to monitoring the spoilage?
Right. So a simplistic factor you can think about is, let's say like what is the contributing agent for your spoilage? So this may be a microbe or it can be a chemical deterioration. So once you identify that agent, then you determine the rate constant at one temperature and determine the rate constant in the second temperature. So let's say 70 and 80, and then look at the values. So if the values come as let's say 3 and 2, then the ratio is 1.5. Then that means that factor is 1.5. Okay. So whereas if I have value 4 and 2, then the ratio is 2, then that factor is 2.
Okay, so you are suggesting that the equation, the Q10 equation that we just saw, each time we are trying to decide on the shelf life, which factor to use, so each time we'll have to put that equation into, we'll have to work with that equation. Is that what you're trying to suggest?
No, like I think that's one way to establish the shelf life. But you as a producer probably need to know what is the thing you're targeting, right? Is it my enzyme spoilage is my rate limiting step, or microbial kinetics is the limiting step, or some textural modification is my rate limiting step. So once you have that knowledge, then you determine that K values, and then you calculate that value, then you can able to estimate the shelf life.
Okay. Okay.
right? Because I think it may be one for one product, a different thing for a different product.
Yeah, exactly.
So it's kind of, you have to look at that. And it's possible it may be also consumer dependent, in some cases, because consumer may reject in one part of the world, but the other part of the world, the consumer may accept it. So you have to kind of consider all those things.
Sure. This was the exact thing I was trying to understand, because I've previously worked on shelf life, and I'm not applying this equation in the industry was a very big challenge, because they wanted it in a specific time. And that was very difficult to achieve. So we actually, I don't know whether that was the right thing to do, but we took a factor of 2 for certain products after studying what ingredients they have and how they are being processed. So the factor of 2 was with a temperature of 45 degrees Celsius and a RH of 65%, and the factor of 3 was 65 degrees Celsius. So I'm not quite sure if that was the right approach to have, but we did conduct sensory testing as well, and that's how the accelerated shelf life took place.
Right. So, I think again, to some extent, food designing, some of this thing, partly very scientific. On the other side, it can be art based on your past experience. So if you are in the field for 20-30 years, you kind of have some sense of, okay, this product going to behave this way versus the other way. Then somebody say, okay, go ahead and use the factor of 3, this will do fine, or go and use the factor of 2. They don't need to study all the details, but they can get that. And then as long as consumers support those decisions, people just follow that, right?
Right, that's exactly what happened.
Right. Yeah. So it's one thing we talk things in the academics, but in the industry sometimes they are under pressure with the time and number of things.
Exactly.
So they have to just to use some rule of thumbs type of thing.
Yeah, that's exactly what we did, and I always wondered, because I had that little bit guilt in me, that I always thought, are we doing the right thing?
Right. Again, it's possible if you do systematically the experimentation, your factor may be, let's say if you choose 2, your factor may be 1.9 or 2 or 2.01, so that when you choose that, it probably seems to be working fine. Even though you did not do the studies, it may be close enough so that approximation of 2 may work out good for you.
Yeah, I hope so too, but we also simultaneously conducted real-time studies.
Right.
So we tried to manage both, but it wasn't, in case of all customers, they didn't really want to spend that much money on real-time. If they got results with accelerated, they were going ahead with that.
Right, sure. Mm-hmm.
Thank you so much.
Thank you.
It just makes me feel good that I did the right thing probably.
Yeah, a lot of times you have theory, but in practice the industry always try to come up with their own version of doing things. So
Yes. Thank you.
mm-hmm.